Hi there, welcome back to the channel. Welcome to another project video. This video is sponsored by PCBWay, and I want to thank them for their sponsorship and the boards, which are here. And this time, I've ordered quite a few. And when I tell you what this is, you'll understand why I wanted to keep a few in stock. I actually need these a lot. Or should I say, I often need these. So I decided to order 10 instead of the usual 5 that I do on these orders. And that means that I will have stock for some time and make quite a few of my friends happy. And the reason is that this thing is aimed at guitarists, but not solely guitarists, which is why I decided to publish this in the Simple But Useful series that seems to have started on my channel. What is this? Well, if we look closely, I've labeled it Electronics Old and New JFET Booster. That really is what it is, but it looks a little bit more complex than you'd expect from a simple JFET booster. It's got trim pots. What the hell is that about? Why would you need trim pots? Why would you need all that stuff? Well, the reason is that I became very interested some years ago in guitar pedals and guitar effects and everything else, and I was building them for my friends mostly because my guitar skills are embarrassing. And if you know any guitarist, you'll know they're never happy with their pedals. They're never happy with their tone. There's always something that's better. There's always something that's missing. In my case, I know exactly what's missing. It's called talent or practice or ability. So I don't have to really investigate that too much, but they tend to do that. And one of the common requests is a little booster or buffer that will go inside the guitar itself, whether it's a guitar or a bass, in the actual cavity where you have the pots and where the pickups get wired, and then will act as a buffer between the pickups and all the tone controls that you've got there, which are passive, and the actual amplification stage, the amplifier that the guitar is wired to. Now you may ask why. Well, according to science, not just myth, according to science, the cables that connect your guitar to the amplifier have capacitance. If it has capacitance, it will bleed off top end, high frequencies. How much depends on your ears and what sort of tone you want and just how discerning you are. And if you do that, what you're doing is you're creating a high impedance buffer or preamp stage at the pickups, at the guitar end, and the signal then gets sent through the cable to the amplifier in a low impedance mode. So it's not susceptible to dropping off the high end, probably a lot of other advantages, but that's the main one. So this little thing comes in really handy, and it's small enough. It really is small. I mean, this thing is what, 4 centimeters by 25 millimeters, 2.5. It's small enough to fit into your guitar, into the cavity. It is actually incredibly effective, as I will show you. And there's a lot more to it than just a simple JFET amplification stage, which is what one would surmise if you look at this. There's actually an attempt to bring the tone or the effect of this circuit to emulate a tube front end. That is a tall order for something this small with one JFET, but apparently it works. And I've done it before. I've done it on various occasions. I've built entire pedals using that concept years ago. Here's one of them. We actually had a logo done. This thing is just a crunch pedal with boost. It's got all the bells and whistles. There's the volume. There's our gain control. There is a mid shift on here. So standard, you can shift the effect of the mid control to various positions on the spectrum. Your lows, your highs, your in and out, and so on and so forth. So you'd activate it or bypass it. This is true bypass. And then if you activate it, it'll go through the circuit and you can put the boost in there. We actually went one step further and did the ramp tone black, which was for a couple of lads who had a metal band. And this thing has incredibly high distortion, very, very good sound according to the users. I think I built about 8 or 9 of these. These were done as a hobby, again, as a hobby. So I wasn't going into production, but we actually gave one of these away. I've just remembered. We asked people to design the front for this, and whoever's design we liked best, we would give them a pedal. And this guy did this. It reminds me of the, what is it? The bourbon label? I can't remember it now. Anyway, you'll probably recognize what I'm talking about if you drink bourbon. But this was used quite a bit, and some of them are still using them. They swear by it. I really can't play with these things because heavy metal is not my thing, but hey, to each their own. So yeah, these things use JFETs. All these use JFETs. There isn't one BJT in here. There isn't one IC in here. So I've been playing with them, and the reason I like them is because they do sound better as an end result. They're not as sharp. They're not as cold or metallic. They are a lot cleaner sounding than the normal BJTs or op-amp pedals that you can build. Now, trying to replace a tube with a JFET is a tall order, but there's a lot written up on that, and I'm going to show you what I mean. The idea of emulating a triode with a JFET has been done for quite a long time, and if you search for that on Google, just Triode Emulator, one of the first things that comes up is this guy, Triode Emulator by Dmitry Danyuk. This is a paper that was presented at the Audio Engineering Society convention in 2004 in Berlin, and this goes into extreme detail. People a lot smarter than me have been looking at this, and I'm just reaping the benefits. But if you go through this, you'll very soon realize that he's basing all the possibilities of emulating a triode with a JFET on the transfer characteristics of the two devices that are pretty similar or can be pretty similar. And he goes into all the math and all the calculations in there. And the idea is to try and find how the biasing will affect the response. And it has to do with the ratio between the pinch-off voltage of the JFET and the Idss, because the JFET is sort of a pinch-off device, just like a normal triode, a tube. So negative voltage closes off the current flow. And he goes into a lot of detail, as I said, a lot more detail than I would need to play around with it. He actually goes one step further, and he's got a part 2, which is another paper that goes even further. The method of accurately emulating a triode behavior and high input levels. And that studies some of the effects that the first paper, or some of the characteristics the first paper doesn't cover. And then there's another paper here, which I found interesting, which is by a countryman of mine. I believe Mr. Zvedo is a university professor, and he takes on from where Mr. Danyuk left off, and he looks specifically at a constant which will give us the distortion characteristics of the tube with the JFET. Now, the basic circuit of this kind of amplifier is very simple. This is it. This is a plain circuit of Class A JFET amplifier. And he takes it one step further, and he goes through, again, some of the calculations that were seen before, and he's trying to emulate or trying to arrive at the same conclusion. And in fact, I believe the magic constant that he comes up with, the 0.84, is very, very, very close to what Mr. Danyuk came up with. But then if you research this further, you get a more user-friendly version. And that is something called the Fetzer Valve by a bunch of guys that are absolutely incredible. They are called Runoff Groove. Now, they published the first paper 2 years prior to this one, and this one was, I can't see the date anymore, but it's been around for some time, 2004. So I think the first one they did was in 2004. And if you go through this page of theirs, it's very, very good. It's runoffgroove.com, and look for Fetzer Valve. It gives you the schematic that they worked on initially. Now, the idea here is that they're trying to emulate very closely a Fender front end. It's based on the Fender 12AX7 input stage, which has a grid block resistor, 68K, 1 meg to ground. It uses half of a 12AX7, as you can see here. The triode in the 12AX7 is replaced with the FET, and where the grid is the gate, the anode or plate is the drain, and the cathode is the source. Very, very close correlation. And if you look at this here, this is exactly the way the front end of that tube amplifier is designed. So they've come up with some values which are very, very interesting. They try to actually follow the same sort of values, source resistor and the cathode bypass capacitor, which in this case is the source bypass capacitor. But then they went a lot further than that, and they did some incredible testing on here. This article you've got to look at, because this is really very, very interesting. They show you how the original Fender input works, and then they show us how they've replaced that with a FET and what the response is like compared to the tube. And if you see that, first stage, this is only the first stage, mind you. If you look at that, they've got this thing pretty much exact, except at a lower gain. That's fine. You can always make gain up later. But the interesting thing is that they go into things here that normally you wouldn't think of, like the Miller capacitance. The tube has got quite a bit of capacitance between its grid and its cathode. In the case of the gate and the source, you put a capacitor ground. This cuts off the top end. It's called the Miller effect. They go to it in incredible detail. But more importantly, this is the good thing about it. They work on the principles that have been developed in those earlier papers, which tell them or tell us what the ideal setup is for these values, for the resistor values. Now, there are two values here that are important. One is the source resistor and one is the drain resistor. It has to do with the type of JFET that you use, but depending on how you bias that, you change the distortion characteristics of the actual JFET to approach them to the same characteristics as what the valve triode would do. And they've given us very, very handy calculations here. I'm not going to go through all this again because I really advise you to do that. But if you go here, you can choose a number of types of FETs, and they actually tell you that you should measure these characteristics. You measure the pinch-off voltage of the FET, the IDSS of the FET, decide what voltage you want. And this is an example. I'll be using a J201. It uses very low current. It's the highest, probably one of the higher gain ones that you can get. You're not going to get massive gain. That's not the idea, but it gives you fairly good gain. Another one that you can use that I used a lot before is the MPF 102, which is probably easier to find. But look at this. You put in the pinch-off voltage, which you can measure, and they tell you how to measure it. You put in the IDSS, which you can measure, and again, they tell you how to measure it. And you do calculate, and it tells us what the source resistor has got to be. Now, in this case, I've probably put a 1K in there. It tells us what the drain resistor should be, 10K. It tells us what the source voltage will be and what the drain voltage will be. So you can set it to where your drain voltage is, in this case, close to 6 volts. It'll tell you what the constant current is, the quiescent current, 0.29 milliamps, very low current, so it works very well with a battery. It tells us what the voltage gain is, which is not that high. As you can see, it's 4.8, which is 13.6 dB. And then it also tells us what capacitor you should use as your source resistor bypass to give you that little bit of a boost at the top end. But as I said, I'm not repeating all this. Go there, check it out. Their description is incredible. This is the circuit they design or they suggest you use to measure the characteristics of the JFET. JFETs can vary greatly one to the other. So the idea is test them. And the fact that I've got two pots on that PCB is basically this over here. This one has got a level here. I don't put that in. I don't need that. I just want this thing going straight into the gate. But this thing, you can adjust it. You adjust the RS, the source resistor, to give you the value that your calculation down below suggests you use, or just something that you like, if you like the tone in a particular position. And then you adjust the RD to give you that drain voltage, again, that you wish to have. If you want to just make this a common source amplifier, that's fine. Again, that's why this thing's so useful. The board that I designed is very, very useful because you can use it for practically anything. But the idea is that you have the values and you can adjust the two pots, the two trim pots, to give you pretty exact values. And then if you want, once you get the tone you want, or you get the positioning, the biasing that you want, you can then remove that potentiometer, the trimmer, and put a fixed resistor to a value close to what you've got here. The takeaway from this article and from this whole technique, if you want to do a Fetzer Valve type of little amplifier, which is not necessarily what I want, I just want to do a buffer, really, or with a little bit of gain. But if you want to do it in the Fetzer Valve format, then read this article. This is incredible. You've got to read this. This is credit where it's due. They've done an incredible job. You've got to read this, okay? Some idiot like me just builds a PC board for a common source amplifier. No big deal. But when you know what you're doing, and these guys do know what they're doing, they've done an incredible amount of testing, they've given an incredible amount of information, you've got to show some respect and check them out. Let me show you the schematic itself and the board and how I took that one step further, and then I'll build the board and we'll do some testing. Schematic is very, very simple. Some of these that you see here are just basically contact points that I needed for the PCB itself. But your signal comes in. There is the blocking capacitor here, which you may or may not want to use. You don't necessarily have to use it, but I do. You've got a 1 meg grid leak. You've got the 33 grid stopper. You've got the Miller capacitor, 220 picofarads is what I've used normally. If you want to make it brighter, you can put in 100 picofarads. If you want to make the sound more dull, you can make it 470 picofarads or even 1 nanofarad. It'll really make your sound dull, but you might want that. You know, the transfer curve can really become whatever you want it to be. You can also omit it. This is the whole idea of the PC board. You can build any format that you want depending on what you want, and you can omit it. And you'll see that I've got, for example, the source resistor here, which is the trimmer, and I've got a capacitor in parallel. Now, why is this? Obviously, you won't use both, but I wanted the pads, I wanted the space on the board to be able to replace that or not have that at all and put the source resistor. So I had to design it on the schematic to allow that to give it space on the board. The capacitor here, again, I've just put 150. That the calculation said 147, I think it was, but I normally don't even put that in, but the board allows you to do that if you want. And then here we've got the same situation. We've got the drain resistor, which is a trimmer, and there's the fixed drain resistor, which allows you to use that if you want. You've got the capacitor there, which is just big enough to allow all sound to go through. Now the end here is going to go into the input of your amplifier, which will be probably 1 megohm. And if it's 1 megohm input impedance, 47 nanofarads will not cut off the top end at all. If you wanted again to cut off some of the top end, you can actually make this smaller. You can pinch the top end. You see, this whole idea of this type of board is to allow you to experiment and allow you to play with all sorts of things. Now, the board is designed for the J201, which is a specific pinout. So if you use a different pinout, you've got to flip the legs around. So be aware of that. Let's look what the board looks like. This is our board. As you can see, it's very compact. You've got your input with the ground in there. This will be the signal from your, usually from the volume pot on the guitar itself. Inside the guitar, that'll be wired into here. You'll have a 9-volt battery connection to here, but this is where the trick comes in. You do not connect the negative of the battery to here. I'll show you the trick. You use a stereo jack, 6.3 millimeter stereo jack, which when you plug in your guitar, switches on the power. But I'll show you that when I wire it up, okay? When you take the plug out, this thing is completely switched off, so it doesn't drain your battery. Now remember, this thing is drawing very little current anyway. You still don't want this chewing battery for no reason at all. You've got the, that's one, which is that one? That's the ground. That's the grid leak. Then the signal comes in through that capacitor, through here, goes to your grid stopper over here, and it goes to your gate. Now, this is drain, source, gate. Okay, so be careful. Drain, source, gate. Remember, this is for the J201. If you put another JFET in there, you've got to change that around. So be careful with that. You've got the Miller capacitor over here. Now here at the source, we've got that source capacitor here. We've got the trim pot over here to set the source resistor. And once you've set that, if you want to remove that and just put a fixed resistor, you can do that there as well. So you use either this one or that one. Same applies to the top here. This is the drain, goes to there, through there, to the supply. And again, once you've established the value that you want on there, you can replace that with a fixed resistor. Your signal comes out here through that C4 and it goes out to your amplifier. It's as simple as that. Here's a very simple LT Spice simulation. And what I've got here is just amplitude 0.6 volts, 1 kilohertz sine wave going in here. And if we simulate that, there's our input, there's the output. So you can see we've got some gain on here. The green is the input, the blue is the output. It's inverting, obviously. Signal going in here, it's the inverted version at the top. If you took it over here, you would actually get a slightly reduced amplitude, but in phase. So you can use it as a simple buffer, okay? This thing has got no capacitor here at the moment. I put 1 picofarad to make it very, very small. If we change this to the Bode plot, this is the Bode plot that's going across there. Now let's have a look at this a little bit clearer. What you can see is it captures the bottom end. This is down here below 100 Hertz. So flat all the way across, flat past 10 kilohertz. The 3 dB point is, that's 14, so it's about there, which is at 22 kilohertz. So this thing's pretty flat across the audio spectrum, and the guitar will only be operating somewhere down here anyway. Now if I change this capacitor here to say 1 nanofarad, let's see what happens. what we have now is, you can see it is cutting off a lot earlier. So the minus 3 dB point, which is at about 11 dB, right, will be at about here, is at 5 kilohertz. So that's made a heck of a difference, simply because I've increased the millicapacitor to way too far, way too big. We don't want it that big, so we should change that. Let's make it 220 picofarad again. And if we take this guy over here and we increase that to, let's call it, well, let's make it a big one. Let's make it 1 nanofarad as well. We do this again. Now you see the 3 dB point. This thing is up to 14.2 dBs, and then 3 dB point is 11, would be about here, is about there, so 21 kilohertz. These two actually sort of work opposite each other. If you make this higher, it cuts the top end. If you make this higher, it increases the extent of the top end. If you make this really high, let's make this 1 microfarad. Actually, let's make this 22 microfarad, like the Fender front end. See what happens. Now we've got this thing amplifying up to 21 dB, okay? It was giving us 14, so there's another 6, I think it's probably 6 dB that went up there. That's what it should be. Now from 21 dB, minus 3 is 18.5. Let's see, where are we? 18.5 will be there. Okay, what it's done is it's just basically increased our gain by 6 dB, and we're up to 20 kilohertz. It hasn't actually extended the back end too much because this capacitor is actually affecting it. Now if I make that incredibly small, if I make that 1 picofarad, which is practically nothing, what do we get? Aha, so you see, this thing just carries on and on and on. We've still got the high gain because we've got the capacitor on the bypassing the source resistor, but there's no cutoff because there's no Miller effect. The actual Miller effect of the capacitance from the gate to source is so low compared to what a tube would be, that this thing is flat all the way to, well, this thing goes as high as 50 kilohertz, and it's still pretty flat. So you really do want that millicapacitor here to just tone it down a bit and control things a bit more. So that's our simulation. Let's build a circuit and put this on a scope and see what we get. And here she is, all done. Not much to it. When you look at a board this size, there can't be that much to it anyway. But what I've done here is I've actually built this to be a test set for certain FETs that I'm going to be using on some of those other boards. I didn't actually have a test set up. I decided to leave this like this. And that's the reason why I've actually used the two trim pots, and I've left them in there. And I've also done something else. Instead of soldering the FET onto the board, I've actually soldered these little sockets. You buy these sockets in long strips and you break off as many as you like. I broke off 3. They solder nicely on the underside, and they allow me to plug in the FET and replace with another FET if I want. But this is all there is to it. I've got all the components on here that I want to have on here. I'm not putting a bypass capacitor on there because I'll be using this, as I said, to test various FETs. This is not the device that I used to test the pinch-off voltage and the Idss of the FET. I'll show you that in a second. This is the device that I will ultimately use when I know what those are. I go into that calculator and run of groove, which is really, really useful. I work out using the pinch-off voltage and the Idss that I get from the other tests setup. I'll be able to calculate what the source resistor is, and I'll set that up with the trim pot. And I'll be able to calculate what the drain resistor should be. I'll set that up with the trim pot, put a FET in there, test if it's working like it should. Okay, so we've got output, ground, and signal, input, ground, and signal. This would be the power connections, normally a 9-volt battery. That's what I'll be working with. And this is all done, and I'll be showing this in a second. But before I do that, I want to show you how I measure the characteristics of the FETs, which are important. I mean, the FETs are so different from one batch to the other. Same reference, totally different characteristics, and I'll show you that in a second. I'll show you exactly what happens if you think you're going to get a group of FETs that are the same. I'm using the J201. I really like it because it's a low current JFET. It's also a fairly low pinch of voltage, so you really can't drive it with a very, very high input signal because otherwise it'll clip on the input. So you would like a very high pinch of voltage. The problem with that is high pinch of voltage, to get this thing all biased properly, you need a much higher supply than 9 volts. I found the J201s work quite well, and also you can still get them. That's the problem with these FETs. You sometimes can't get them. The 201s, I'm still finding. They sell them in SMD packages as well, if that's what you want to do. I know most of you don't. But let me show you how I test the characteristics of the FETs. When I was regularly building pedals, I used a lot of FETs, and I built this up. This is more or less what's on that Run of Groove site as a test circuit. I've made 2 rows so that I can use the drain source gate configuration, and this one is drain gate source, I think it is. I've written it there. It's almost completely faded. But at the moment, I've got a J201 in here. That's the row. That's the row of pins that corresponds to the J201 in that configuration. And I supply voltage to here. Make sure I get that right. 10 volts. I've configured this for 10 volts. I've wrote 10 volts there. It doesn't matter what you use as long as you test between one and the other with the same setup. And then I've got this here so that I can connect my multimeter. This was really rudimentary, really simple. Connect the multimeter, and now I can switch between pinch of voltage and IDSS. As soon as I supply this, you'll see what happens. I'll show you the multimeter as well. So this is set up. I'm not sure what's going to test first, but I switch on the power and we are testing pinch of voltage. It's got VP written on there. And what I get is 0.96. Call it 0.96. Now, if I hit the button there, this is holding, I get 0.094. Now, the way this is set up, there's the red light telling me that I'm measuring the IDSS. The way this is set up, I've got to multiply by 10, so it's 0.92 milliamps. So 0.92 milliamps. I've got to write that down because I'll need that when I go to the Run of Groove calculator. Switch off the power again. And that's one JFET. This is another J201. See what we get. Switch the power on. And now I'm measuring, oh, that slipped out. That's measuring IDSS. And here we see a completely different setup. We see, oh, this is not holding properly, hang on. So 0.56 takes a little bit of time to stabilize. So it's 0.57 milliamps. And if I hit that, measure the pinch of voltage, 0.781 volts. See the difference? Quite a difference. The pinch of voltage is close, but the IDSS is dropped from 0.92 on the first one to 0.57 on this one. So that's quite a difference indeed. I'm going to plug those values into the calculator, and I'll plug that into the test circuit, and we'll be ready to see what differences we get. Right, I'm on the calculator on the Run of Groove website, and I'm going to enter the values. I rechecked them, I recalculated them, gave it more time for the values to settle, and the one I've got is 0.96 volts. And the IDSS is 0.85 milliamps. And 9-volt battery. Calculate. And that tells me that my RS is 937 ohms and my RD is 7496 ohms. The other thing that's important here is that the VD, the drain voltage, should be about 6 volts. And also the gain is 4. I'm just writing those down. Now if I go for the other one, it's 0.82 and the IDSS is 0.52. Calculate again. And I'll make a note again of that, which is RS1309, RD 12738, and then my VD should be 5.97 volts, and my gain should be 4.9. So we'll see. We'll put that in the circuit and test it with a scope and the signal generator. See if we get close to these values. Now, without a FET in there, I take the FET out, connect my multimeter leads to ground and to the source connection, which is the middle one. And I'm going to adjust that trim pot. I need 937 ohms. Or thereabouts. I've got a 1K trim pot over here, so that should do it. I should have put a 2K trim pot because if I need greater resistance on there, that won't reach, but that's fine. The other one, the drain, goes to the positive lead, so to the supply. And in this case, I need 7496, so 7.5K, for example, there. So I go to the drain pin on there, and I want about 7.5K. It's too high. So I'm going down 7.5 or thereabouts. I mean, this thing doesn't have to be absolutely exact, but actually we've come up with some pretty exact values, pretty accurate values. Now I can put in the JFET, the one that I've pre-programmed the trim pot values to, and my circuit is ready to be tested. So I'm going to connect this to 9 volts. I'm going to connect a signal in here. We'll see that on the scope, and we'll see the output as well. We'll be able to see what the amplification is like. We'll see what gain it's getting, and we'll also see how this thing acts in terms of distortion. I'll be increasing the amplitude of that so we can see what sort of distortion characteristics we get there as well. So this is what we've got. I've got 100 millivolts RMS coming in. That's the yellow trace you can see on the screen there on the scope. I've got the output here going to the purple trace on the scope. I've got 9 volts coming into here. Shouldn't touch that, should I? And it seems to be working pretty well. The actual amplitudes, if we look at the scope measurements, are 108 millivolts, 100 millivolts input. This thing is not really that stable. 100 millivolts coming in and 296, so 300 millivolts coming out. So we've got a gain of 3. Not quite what they told us to expect, right? I mean, they said the gain was about 4, I think it was. Yep. They also said that the voltage at the drain should be 6 volts. So let's see what it is we've got. Connect this to ground. Test the drain. 7.46. You see, that's not the way one expects it to go. But what you can do now is you can actually change the voltage at the drain, and you're moving away from the ideal triode situation. But what it will do, if I drop that to say 6 volts, I've got to tell you, in a lot of I'm going the wrong way. A lot of these, I actually set it for the half the supply voltage, which gives it the biggest swing. Now, what it does then is it gives you the greatest headroom before it clips, before it reaches the supply rails, and it gives you more gain. But it does move away from that whole idea of emulating the tube exactly. Now, I wasn't even looking at the scope. Let's see what's happened here. That thing's now gone up to 572. So now the gain is 5.7. It's even more than we expected. And if we take this thing halfway, if we take it to the halfway mark to, what is it, 4.5 volts? Which would give it the biggest swing. About there. That gain is now 7.8 or 8. We're getting 800 millivolts coming out with 100 millivolts coming in. That's peak to peak. So we're getting a gain of 8, and that's now at midpoint. But let me take it up to 6 again, because I want to try the distortion situation. I want to increase the amplitude of the input till I get, let's leave it at 6 volts. See, the beauty of this is you could actually be listening to this. Let's leave it about there. And now what I'm going to do, This is the output waveform. Well, let's leave it down here. We know the gain there is about 5.7. Now I'm going to increase the amplitude of the input signal. It's at 100 millivolts peak to peak. I'm going to give it 200. Oi. That's the input one. That's the output one. These are not on the same scale. I'm getting 320 millivolts coming in, 1.7 volts peak to peak coming out. Now let me carry on. Change the gain again. We've still got a good sine wave. 800 millivolts, 9. This is 1.1 volt, 1.2 volts. And I'll change the range there as well. 1.3, 1.4. And there you see it starts clipping. And it's actually starting to distort. The output waveform is starting to distort equally on the top and the bottom. A little bit more at the bottom than at the top. But this would give us some pretty good harmonics. The sort of sound that a lot of guitarists like. And this is right on the first stage. So if you've got a very hot pickup, it can reach 1.6 volts peak to peak. And that's the kind of distortion you get. And then, of course, if you carry on, it's squaring off, but it's not quite square. It's sort of slightly rounded off. I think that's already at the supply rail. That's why it's squared off completely. But we could probably say that the usable range is 1.5 volts peak to peak with this JFET. Now let's change the JFET and see what happens. I'm going to switch the power off. Switch the input signal off just for good measure. I'm going to take this JFET out and I'm going to put the other one in. But again, what I've got to do now is I've got to reset those resistance values because we had a different setup for that. And what we had for that was RS1309. Oh, that's a problem. I can't get that high. I've got 1K maximum here. But I'm going to put it on the maximum anyway. That's why I should have used a 2K trim pot. That's as far as it'll go. Damn. Okay, well, let's see what the top one is. Top one says the drain, it should have been 12.7K. This one will reach quite easily. $12.7K, okay. We'll put this one in and see what the signal looks like and where it distorts and so on, what gain we're getting. All right, okay, let's have a look again. Switch on the supply. Switch on the input signal, and am I doing something wrong? Yes, I am. I'm being stupid. I don't really have the supply on. There we go. Okay. See, our distortion is now different. I've got it at 1.5 volts, the same input, but I'm getting more distortion at the top than the bottom. And now my useful range is 1.1 volts. And the gain, let's take it down. The gain is 720 millivolts peak to peak. Let's make it a round number. Let's go back down to 100 millivolts. And the output is 5.6, so gain is 5.7. Go figure, this thing said 4.9. So let's have a look at what the drain voltage is. 7 volts, again, a bit high. But if I take that down, say to 6 volts, about there, our gain is now up to 7.6, same as before. Anyway, the point is you can see how different these FETs can be, and this is just two J201s. If I change this to the 2N5457 or 58, which I've also used in the past, this thing will change completely. The biasing is to be changed completely. The way this works well. The J201s work well for me, and that's usually what I'll stick with. If I was using this kind of amplification stage, say after a tone stack, then as I did with that pedal, then of course there would be a different configuration, different biasing, and the setup, the biasing wouldn't be as critical as it is here. But that's what it is, and it works very, very well. And let me show you how to set this up so that it switches on. I'll leave get rid of what I don't need. I don't need the input signal. I'm going to leave the essentials, and I'm going to show you the switching situation here, why you don't need a switch on this if you put this inside a guitar. It's actually very simple, but it's very, very neat how that works. Now, the way this works is by using a stereo jack on the output from your guitar. Instead of using the normal mono jacks where you'd put a female and then you'd have the male plugging in, this would go to the amp, you use a stereo jack. And the way you do this is you take your signal, your output signal, that goes to the tip, right, to the end here. So that'll go to, let's put this in, I'll show you. These cliff jacks are really tight. So that signal, the output signal, will go to there, which means it'll be fed to this point here, which means it'll be fed into the tip of the jack, of the male jack. Then the ground comes to this one here. This one goes to the output as well, and this is obviously connected to the ground here. But then what you do is you take your negative supply, and you don't connect it to that ground, you don't connect it to the tip, you connect it to this guy over here. And it's that one there, all right? Let me connect these as if I'm connecting the guitar out. That's my ground. Okay, there's my output from there. That will be soldered to the ring, to the tip rather. So that'll be soldered to that one there. And then what I do is, I take the ground of the supply and I connect it to that guy over there. That one over there. Now what happens is, when I plug it in, see that? It switches on. That's not connected at all. And the reason is that the power ground, the mains, or rather the supply ground and the audio ground is the same point. And all I've done here is, because I've taken the ground of the supply to that middle connector, the middle pin on the jack, I have forced, by pushing the jack in, I've actually switched the two together. I've switched this point here with the ground point together because this thing is one solid connection. So when I push it in, you do it a lot faster than this. This thing is really tight. Bloody hell. Okay. When I do that, I am switching the ground of the supply into the circuit, into the ground of the circuit, whereas normally you'd have a switch on the positive supply. But that's how these things work. All the pedals work like this. A lot of the active pickups in the guitars that have an active system like this or similar work like this, so that you have a battery in here, a 9-volt battery. The positive of the battery goes to that point there, and the ground of the battery, the negative of the battery, comes to this point here. So every time you pull your guitar out, your internal electronics is completely switched off. That's really it. Not much to it, but it's a really nice, clever way of saving battery and not having to make another switch on these guitars. You don't want to make holes in the front of your guitar, the back of the guitar. This is a really neat way of doing it. And even if you forget this in for a while, this thing is drawing so little current that it'll take ages to drain your battery. Mind you, people do forget these things connected, but normally you don't. And that is it. That's our little JFET Booster. Very simple, rather bulky the way it is here because I've left the trim parts in, but you can imagine if you build this thing on a normal board, on another board, without the trimmers, you can bias them and then remove them and replace it with a fixed resistor. This thing can actually be quite small. The capacitor over there is not absolutely necessary, but I like to put it there just so that smooths out any ripple that you might get. You're not going to get much from a battery anyway, but just for safety's sake, I normally put them in. This is going to be my test unit, and all these others are for my friends who have guitars, who want active systems in their guitars. And I know what I'm getting myself into. Now they know, they're going to see this video, they know I've got these boards, and I'll be getting calls very, very soon. I tempt them, I've got to satisfy them. And I hope I've tempted you to give this a try if you want to experiment with JFETs, or if you want to actually build it for a purpose like I'm doing here. This is a very useful little thing and something I've been using for a long time, and finally found the simplest way to do these things, which is to prepare a board and have it ready for whenever I want to reproduce them. I'll be sharing these boards on the PCBWay share section, so if you want, go ahead and order your own or download the Gerbers, whichever you prefer. And I do hope you've enjoyed this video. If you have, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon and PayPal. Thanks for watching. Bye for now, and stay safe.